Alright, so this video is the first video in a series about 4.1 where we're learning about linear approximation and applications. Big idea. We're making functions that are not kind, that have a lot of intricacies, that are difficult to solve for, what have you. And we're going to use linear functions to force that icky function to be linear at a point. And then we're going to use that small area to figure out what the function is at that point. So in essence, let's say we've got this curve that's happening, like so. But let's say I'm not really interested about this whole curve. Let's say I'm particularly interested in the curve at that point. So what I can do is I can draw a tangent line. There's my really unfortunate version of a tangent line. Do a tangent line at that point. And I can use that pink area of the tangent line to figure out what the function is doing at that point. If, let's say, this function, f of x, is really problematic in terms of whatever the function is. Like, let's say it involves lots of trigonometry or something else that we just don't want to solve for. If it's easier, we can kind of create a linear function and say, all right, this linear function is a good enough approximation in that area that's in the pink to allow us to solve for things about f in that pink area. Now, I do need to point out that there's a whole bunch of space in here. All that space. The farther out from that pink area that I get, all that blue stuff is error, right? That's where the linear function doesn't match what the actual f of x is doing. That's where the linearity, at least in that pink zone, stops. It's no longer appropriate for me to use that linearization, that red line, that pink line, to approximate what f is doing, because all that blue, the farther away from that pink zone that I get right there, the farther away from that pink zone I get, the more error that I've got when trying to use that line. So if I wanted to move out, it would be more appropriate for me to create another linearization, another tangent line. Let me do this one in blue. Let's say I was interested in that zone now. Then I would do another linearization. Let's see if I can draw. The line function on this doesn't work very well. So that would be another linearization where now the error that I've got crack-a-lackin' is there. All of those icky spots. So 4.1 is all about applying a linear approximation at an area, and it's basically using that idea of linearization or linearity, creating an area that when we zoom in far enough, it is fairly linear, and using that linearity to approximate. Basically saying, in that pink zone, the function is fairly linear. So I'm going to create a linear function there to approximate that area of the function, appreciating that if I move too far away and the linearity behavior is not happening in the area where it was blue or the area where it's pink, it's not going to work anymore. Okay. So the function that we're using, this is the fancy. When you're using a linear approximation, they go ahead and change it from like another f of x, and they call it L of x. And that L of x indicates that this is a linearization. And this is f prime of a, x minus a, plus f of a. Now, I want to point out that this is a point slope version of the tangent lines that we've been using all semester. So this part is not scary. All you're doing is attaching at some f of a, where you have an a f of a, you're going to find the derivative at that point and create a tangent line using those areas. That's all you're doing. And then we can use that to approximate other things, some pretty cool things, to kind of allow us to work with a function that may not be really friendly otherwise. This is a first level in what we call Taylor polynomials. This is a first level Taylor polynomial. And so this idea of using this approximation will come back to us at the end of second semester when we actually do that first level of Taylor polynomials. And Taylor polynomials are where your third quarter calculus class So once you leave me, your third quarter calculus class will pick up is right there. Okay, first thing I want to do is I just want to do some linearizations at some points. So I'm going to give you 4 functions, and then I'm going to pause, and you're going to find the linearization at a equals 1. So f of x, let me put it in black, f of x is equal to e to the x minus 1, and then g of x is equal to x to the 4th minus 3x plus 2. And then we have a third, h of x equals ln of x. And fourth, j of x equals 2 over pi sine pi over 2 x minus 1. All right, and what I would like you to do is I would like you to find the linearization which means the L of x at a equals 1. So that's how your instructions in your textbook are going to read, but what this really means is find tangent lines at a equals 1, which you've been doing all semester long. So I'm going to pause the video here, and then when I restart it, I'm just going to go ahead and show you the answers. If you need this support, just hold tight and the video will come right back on. If you don't need the support and you want to pause it here and try to do it on your own, you're welcome to. Okay? So what you should have found at this point is that your linearization for all 4 of them are the same. L of x equals x minus 1. Curious that they all 4 had the same linearization at that point. That means that their linear behavior at x is 1 or a is equal to 1 is all very similar. All right, so I went and recorded all 4 of these functions into Desmos just so we could get a visual around x equals 1. So that's where I'm at. That's my domain, 0.96 to 1.04, very small domain. And we can see that the polynomial, which is the one that is in blue, from what I can see, sure enough, the blue is the x to the 4th. So that is the one that differs the most from the other 3, and it has the most error as you get away from 1. So there and there. Okay, so the other 3 are actually very similar in their behavior around 1. So that's why they all have the same linearization, is because right in, I would say right about from here, they're darn near identical. If I would have zoomed in farther, those 4 functions would have looked almost similar. So that's why the linearization is the same. Okay? So now what I want you to do, so what I'd like you to do is I'd like you to fill in this table. We have the function. Function. And we have, I want you to find the function at 1.1, and then I want you to find L at 1.1, which will be the same all the way down, right? And I want you to fill in this table for F, G, H, and J. Okay? And L of 1.1 is, since it's just x minus 1, is just going to be 0.1, and that's going to be the same for all of them. Okay? So what I want you to then do is I want you to figure out what 1.1 is on the calculator for all the remaining 4 functions. And what we're going to do is we're going to examine error. Okay? I'm going to pause. All right, so what we did is we're using that linearization at 1 to go 0.1 away from that linearization. So that's what we've done. We've used the linearization at 1 to go 0.1 away. And then we put it into the function so we could examine the error. And so it appears that we have a big error at some places and smaller error in others. So if we examine the change between 0.1 and all of these, absolute, because we're just looking at error, distance away from the true value. So this is what, 0.0052. This is a super small one, 0.0004. And then we have this one at 0.0047. This one is 0.640641. So the best function in terms of this was right here. That had the smallest error. And the biggest error is right here. And do you recall that the biggest error happened to be that polynomial, g. G is the polynomial. Remember, we could see that happening before we even did anything with it. So it's no surprise that that blue zone, the biggest area, is the worst, because we could see that happening on the graph where we could see it curving up. So the farther away we move from that one, the worse the behavior. And we were super far in. We were, I mean, I think it went from what, 0.96 to 1.04. So I mean, we were less than a tenth in terms of the distance there. So or not less than a tenth, just a little over a tenth. So the linearity problems would be exposed in that graph with that domain written as it is. All right, I'm going to cut the first video off here and move to the second in the series.